So we have Will and Ron doing, I guess, two separate presentations. One is kinematics of line following, and the other one is you did like simulations for line following, right?
Yes, and also a interactive line following course, builder tool that I'll show off. Although maybe it's something that's not needed, but I'll kind of explain part of that when I'm up.
Good.
Anyway.
Okay, take it away.
Okay, let me get your agenda there.
All right. Well, our talk hopefully today is to talk about the kinematics of line following, and I separate that from the actual problem of finding the line. In the challenge course, there's no line on the board, so you have to somehow combine the line. So, but what I want to talk about is some of the dynamics of how you follow a line. And basically, the reason I decided to give this talk was it appeared to me, and seeing what other people are doing, that they kind of ignored or this aspect of the line following.
Yeah, specifically me.
And I guess the way my talk is going to run is I'm going to describe my robot T2LS, which I built surprisingly a long time ago to follow the tabletop line following contest, DPRT, which is real simple. It's basically just a closed loop that had a couple of 6-inch turns in it. What I'm going to do is describe the robot, and I'm going to try to tell you why I did what I did, and then I'm going to try to tell you just a couple of little lessons I think I learned, and then I'm going to speculate on what it might take for the new course. And I had planned to give you some references, but I ran out of time, so.
We can add those later.
Next page, please.
All right, I'm the semi-intelligent page advancer here.
Voice operated.
Voice operated.
And we'll be the
it.
judge of that.
Yeah.
Okay.
Okay.
Designed for the tabletop line, it's intended to follow a 1-inch wide line on a black background. It was a continuous curve with no sharp corners or anything in it, just 6-inch radius.
And that was like how many years ago? Like 5, 6 years ago?
How long ago was it, Clay?
It goes back.
That's a good question. Probably 10, 12, I'm not sure.
Probably at least.
I'm going to say about 2016, 2006. 2005.
And I think that's what we call the novice course now, more or less, right?
Well, it was actually built on a table. It had a wall around it.
Yeah.
Okay. It's a small robot, approximately 6 inches. But you can see what I said. It's about this big. In fact, this is it. I have modified it a little bit for other purposes, but this is it. It's primarily made out of plywood, and the reason for that is my previous hobby was flying, designing RC airplanes, and I'm well equipped and knowledgeable how to handle plywood. Besides that, it's easier to work and stronger than plastic. All right. It's a 3-wheel. It's got 3 wheels, which is, and the front wheel here is steerable and drivable, has a motor on it, which is a little different from most robots you see now are differential drive. I guess there were several reasons for this. One of them is when I built this robot, I wasn't comfortable with trying to come up with a PID loop. And with differential drive, you got to have 2 PID loops. With this kind of arrangement, you don't really have to have a head loop on the motor because it runs pretty much constant speed. You know, used an RC servo to steer it, so I've sidestepped a lot of problems that I would have had. All right. The drive motor, a little thing right here.
Yeah.
And I think that come out of the camera. I bought it from All Electronics. It doesn't have an encoder on it, but I put holes in the wheel and have a pair of LEDs and a sensor, so I can at least do some kind of rough encoding. It's got a H-bridge with some nice old metal can transistors on
What's a transit now? I'm kidding.
Yeah.
it. Okay. And as
It's
I
not a
said-
vacuum tube?
No, I couldn't quite fit my vacuum tubes on here. And as I said, there's an RC servo in there driving. Power is 6 AA NiCads. There's a pocket under here that's got 2 of them in it, and there's a pocket over here that's got 2, and then there's one of them across the bottom. The brains is an Admiral Omega 8 on a proto board that Dale Wheaton was selling at the time. So it didn't have a whole lot of horsepower, but the board I could handle anyway. It's programmed in C and with a ad that was available at that time to the club called Atlan. And I used a parallel programmer, which one of the club members gave me a schematic for, and I built up. Okay, next page.
All right.
All right. The line sensor is kind of interesting, I think. I'm going to pretty well let y'all read what I said there. But that is the line sensor. And my object was I wanted an output that was continuously variable, that was proportional to the how far I was off the line. It has a little box with divided into 2 compartments, and there's a cadmium sulfide cell in each compartment. And there's 4 LEDs, and there's a separation between them. And then the LEDs illuminate the course, and depending on how much of the aperture on the bottom there is on the line, depends on how much light is reflected. And so it gives you an output. Cadmium sulfide cells are hooked in series across 5 volts. Midpoint gives you the difference. It turned out it wasn't exactly linear, so I wrote an equation to straighten it out. All right. One of the things about the sensor that turned out to be bad is that as long as you're within over the line, it gave you an output which is more important. But what happened is when you got completely off the line, the signal would actually drop again. And it turns out that's bad news. You'd really rather have it stay constant or anyway. All right. And then one unique thing, I guess, about this robot, probably the most unique thing, is that the line sensor was mounted between the rear wheels. And the general opinion, at least at the time when I built this robot, was that the line sensor needed to be in front of the wheels. And so basically, I guess, what it turned out is that yes, I can make it work with the line sensor between the
Right.
wheels, but I had to have derivative control on the next line. All right. When I started designing this, first thing always in a design project is you kind of go see what the current state of the art is and this sort of thing. So I went back to basically the state of the art back in mid-1950s. I had the privilege of going to a machine tool show in Chicago, and Cincinnati Mellotron were displaying their brand new line following milling machine. And these were the samples they gave out. They machined each one separately, and
I can pass it here. Oh. That's tight.
they'll come apart. There's no problem there.
It's-
Anyway, I'll say that, I thought that was kind of interesting, but, well, I thought,
So they would just draw a line on the part?
they drew a line on a piece of paper, and then set it down, or set it on the table, or, or planted on the machine. And the machine followed it and actually milled apart.
But the
The paper.
paper's separate from the.
Yeah.
Yeah, okay, like a Panamill sort of,
Yeah.
however you call it. But,
Yeah.
but real, like,
So I guess
So
that allows you to
likely
do
would-
free-form design, kind of?
Yeah, just
Yeah.
free farm.
Nice.
Yeah. Huh.
Pretty accurate too.
Yeah, it's pretty accurate, and that,
Yeah.
So this was back in, like I say, about 1955, somewhere along there. Well, I don't remember exactly how they did it, but I thought they had a CRT that was generating a circular scan, and the lens projecting that down on the paper and looking at the reflection off of it. So I collect old magazines. I had a subscription to Control Engineering magazine back then. So I decided to see if I'd saved some of the old articles. I decided to see if I could find the article. I said, find an article, but I didn't. But I ran across another article for a flame cutting machine. In other words, they use a cutting torch to cut out steel parts. And this was a design for how it worked. I thought that was interesting. Kind of off the subject a little bit, but interesting. You notice the servo motors back then, they very seldom did use, they didn't tend to use PC motors. They used two-phase AC motors. And on the two, you're familiar with it. On a two-phase servo motor, you put a fixed voltage on one phase, and then you put a variable voltage on the other phase, and how fast, what, whether it was no voltage or actually changed 180 phase. That mean?
no.
Anyway, these had phase, and it made the interesting thing about this is the line sensor. Apparently there's a photocell, and apparently it's kind of got an arm that hangs down, and the photocell's on the bottom of it, and there's an electromagnet up here which made it swing back and forth, and then there's a lens that projecting an image up onto the photocell, and it sit there and swing across it. And the interesting thing, that would generate a waveform that had a notch in it where the line was.
Yeah.
The interesting thing to me about it is how they generated that control winding phase. It turns out that if you got a symmetrical waveform, you do a Fourier transform on it, you don't get any of the signal necessary to drive the motor. But if the notch moves off, it becomes unsymmetrical, and that introduces the control signal. And also the other thing you notice that the steering motor's got a tachometer on it
Okay.
rather than an optical encoder.
Mhm.
And here's another important difference. You notice that they're using a steering motor, which basically says that the speed of it is more or less proportional to the arrow. Where on this servo, the angle is proportional to the arrow. And that, well, I realize most people use differential drive. What that's, as far as I can tell, what that basically means is that if you use differential drive, what you, to accomplish essentially what I have here, you have to have a velocity loop around each wheel. So you need a speed control on each wheel, and then your arrow drives the difference between those two speeds. Next slide. All right. The next thing I investigated, or what I did, was how long should the robot be? There seemed to be an opinion at that time, at least by one member, that the longer the better. But I did a few things to try to understand what might be the better choice. And so basically one of the questions I said is if I set the robot down, where it's not on the line, but the sensor is on the line, and the sensor follows the line, how long does it take the robot to line up with the line? And that's what this diagram here shows. The top diagram shows the three-wheeled robot in a start position and an end position. And the robot's 5 inches long, and it's offset half of that. Front wheel is on the line, and then the robot moves forward 5 inches. That's the length of the robot. And the green line shows the path that the robot takes. And you'll see that it went down about 63% of the way towards the line. And then the next one is basically just a continuation. And the next 5 inches that the robot moved, it moved another 63%, that is, of what it started out, for a total of about 89%, which says that if the robot starts out at an angle like that, it's going to be pretty well lined up when the robot has moved 2 lengths. And I felt this was important because I kind of felt that each time the robot came to a change in the path, that is from a straight line to a curve, that represented a step input to the servo. And I felt it was probably a good idea that the servo kind of settled out before it hit the next curve. So that next slide. All right. So the next thing I said, well, what happens when you go from a straight line to a curve? And what I did, I drew it here for several different radiuses. The big one here is a 10-inch radius, which is twice the length of the robot. And it starts out at the top straight. And then you can see the green line, and it settles down to a circular path, which is offset from the path. But it settles down, and it looks like roughly a quarter of a turn, thereabouts. But then the next smaller one there is a 5.5-inch radius, which is just a little more than the length of the robot. And you'll see it does settle down, but the robot has to go almost 3/4 of a circle before it turns before it settles down. And then the next one is what happens if the circle radius is smaller than the radius. And the answer is it kind of goes crazy. In fact, the matter, you'll see it will go around until it finally gets to where the robot is basically perpendicular to the line, which is another important point. If you got a line sensor that's a straight line, your line sensor is now not perpendicular crossways your line, it's lined up with it. So basically,
Doesn't know where to go.
doesn't matter. So I guess next slide, yeah.
These diagrams are great. I love this analysis. I'm just curious what you drew these, or how did you get these graphs?
It's a trade secret.
No, I'm good. Well, if I was a guru like this guy, I'd simulate it. And since I'm not a programming guru, and at that time particularly, I'm not very much a guru, what I did is I got me a piece of wood.
Excellent.
And put my wheel on the back of it, a stick on the front of it, and I drew me a path, and I held it on the paper, and I followed that line with my pointer and watched what the wheel did.
That's a simulation, by the way.
Yeah. That's beautiful.
So that's what, actually, I did that a long time ago. And I lost it. So I built another one. This time I got fancy. I actually made a common triangular shaped piece of wood, put two wheels on it, and a nail for it. And then I drilled a hole and put a pencil in it, so I could put it on there and trace it around.
Draw the path.
Anyway, that's how I did it.
That's
good. Awesome.
And you know, the interesting thing is, what would take longer, him to construct something like
Right.
that, or me to try to write the code to simulate it?
Yeah, I'm not going there.
He's got it all
He's
done.
got it done. He's got it done, and on to the next project when you're just getting started.
Ron's still trying to spell Delphi.
So the result of all of that was I decided that probably a good idea to make my robot about half the radius that was on the course, which was 6 inches. So I made my robot basically 3 inches from here to there. So that's one decision. Next slide.
He basically future-proofed his robot for tighter curves.
Yeah.
But then along came the broken, disjointed nightmare. So Will decided he was fed up. I'm talking.
All right, the next thing I begin to think is basically about the stability of the servo. Would it oscillate? In other words, if I made the angle of the steering proportional to the arrow, would the servo oscillate? And I suspected it would. And so I graphically determined that it was unstable. And for you, Clay, the way I graphically determined it, got on AutoCAD, I drew this robot there, and I said, okay, it moved, in the direction the wheels are pointed. So I moved it a little bit, I drew it again, moved it a little bit, drew it again. And I started off, with off, and it, I think I had a curve. And it went along here, it closed in on the curve, it overshot the curve, it went beyond the curve back, and overshot, and each time it overshot, it got further away.
Yeah. Oops.
So I figured, well, it's probably going to be unstable. All right, so basically, what I did back in the 50s when I was in college, I took a servo course. I'm not sure I learned a whole lot about it, but I got a book out of it. And so one of the things I did, I sat down and kind of reviewed the book as best I could. And back in those days, it was talking about frequency domain analysis. And for at least one of you in here that don't know what the frequency domain is all about, The reason I want to mention this is because I think it brings out a couple of points that are kind of interesting. Basically, one of them,
Yellow poles and zeros.
yeah, there's a line there where I got sine wave and arrow and a controller and a plant. What I did that word, and I tried to draw a box around those controller and plant, and I wound up erasing my work.
Yeah.
But anyway, what I'm trying to show there is, if you take your servo or your plant, by the way, plant's a fancy word several people use for actual robot, the mechanics of it. Okay, if you have the actual plant, put the exact robot controller in front of it, and you took a signal generator, and you fed that signal into the, it's closed loop system, but you broke the feedback loop, so it was open loop.
Yep.
So you feed the sinusoidal signal into it, and you look at the signal coming out.
Yep.
Okay, the signal coming out is going to be the same frequency as what you put in, but it's going to be a different amplitude, and the phase is going to shift. And quote, low and medium frequencies, amplitude will vary around and everything, but eventually it starts nosediving. And so basically, as it starts going down, the amplitude goes down, and the phase shift lags further and further behind it.
Okay.
Some frequency, the phase shift is such that it's 180 degrees phase shift. So when you connect the loop, what you thought was negative feedback becomes positive feedback. It's an oscillator. So the thing is you want the amplitude to be, of the system like that, to be less than 1.
Yep.
When the frequency goes to 180.
When the face is one.
So that's the concept of frequency. So the problem is then, how do you design this controller, which is a filter frequency? How do you come up with a filter that manages things and makes your loop stable? And one of the main reasons I brought this out is to emphasize that any delays in the time it takes you to look at the line and come up with a command for the motor is a delay.
It's a lag. Yep.
It's a lag, and that's bad.
Oh, yeah.
If you put it in a circle loop, that's bad.
Oh, yeah. Yep.
Okay. Now, the proportional, basically when you add proportional to your controller, it increases the amplitude, but it doesn't change the phase. So if with a low proportional number, your system is stable, and you start jacking up the gain, sooner or later, you're going to get the gain out here enough to where it's going to oscillate on it.
Yeah.
So, but you'd like that gain to be high, because the higher it is, the more accurate your servo is going to be. All right? So what does the integral do for you? Well, what the integral does for you is it increases the gain at low frequencies, or DC, when it's stationary. It increases the gain at low frequency, but doesn't particularly bother you at high frequency. And what the derivative does, it doesn't seem to do much with the gain, but it causes a decrease in the lag. So by punching in some derivative, you can reduce the drag, the lag, and up the gain.
Yeah.
So that's basically the concepts basically that I want to present.
The practical way of thinking of it.
Yeah. In my experience when I was going to college and doing tech work at JPL, we had a table that we would put a gyro on, and if you close the loop on it, it would track the Earth's rotation. And I found that you crank the gain up and it goes, you crank up the tachometer, which is your derivative, and it would stabilize. After seeing that, I said, okay, I better take a circle course.
Well, so after looking at this, I said, well, maybe I better try to figure out what design this servo. So I tried to come up with a math model to describe what the mechanics of this was as it moved. And it turned out that if you put the line sensor between the rear wheels, the plant basically looks like two integrators in series.
Oops. 180 phase shift.
That's right. Basically, an integrator gives you a 90-degree phase shift. You put a sine wave in, you get a cosine out, or vice versa anyway.
Yeah.
So you get so I've got two integrators. I got my 180 degrees phase shift at all the frequencies.
Yeah, yeah.
So it says I had to have it derivative. Also, came up with a math model for having the line sensor ahead of the line, ahead of the wheel. And basically, as best I can tell, is that what the effect that did was to kind of put some feedback around one of those integrators. And what the effect of that is it keeps the amplitude more or less constant out to a certain frequency, and then it drops off. And so basically, that is basically the equivalent of putting some derivative into your controller. So basically, it says by moving the sensor forward, you kind of incorporate some derivative in it. Now, whether it's enough to make it stable enough, who knows?
Yeah.
But anyway, and I may be wrong on that, but that's what I feel. Let's see, where am I? All right. So I guess my conclusions were basically, it should be possible to put the sensor behind on the wheel. And let's see, what else did I include? If you make the steering proportional to the era, you come up with a Type 2 servo. Now, what's a Type 2 servo? Well,
Velocity.
well, basically, it's kind of one of the answers is how many integrators do you have in it? So that I've got two integrators, so it's a Type 2 servo. But there's the other kind of definition of a Type 2 servo. A Type 0 servo is if you have a constant input, your servo requires a constant output. There's a little error, a constant error. In other words, if you're trying to heat the room, you got to have a little difference to keep the furnace on.
Right.
So a Type 0, there will be there's a constant error if the input is 0. A Type 1, you have a constant error if the input is around, linear around. And a Type 2 is that you've got a constant acceleration. Well, it turns out that going around a curve on the course is a constant acceleration. So it says it needs to be a Type 2. The other thing is just looking at the robot. It says if I'm going to go around a curve, I've got to maintain a constant steering angle. So I've got, if the steering is proportional to error, I've got to have an error. So basically, all of that says it's a Type 2 servo. And that's why I call it T2LS.
Yeah.
Type 2 linear servo.
There you go.
All right, where are we at?
Next page.
Yeah.
Well, maybe move it.
Okay. I already said that.
Okay, okay.
All right. Next thing I did was I wrote a very simple program to try to simulate it to see whether it looked like it was going to work. And it was very simple, let me assure you, very crude. I think I just had a straight line with a curve, which I entered in the program as an equations, basically. And then I approximated or simulated the surface robot, which or not using odometry. And for the output, I didn't have a nice fancy graphics output. All I did was print out the arrow for each time step. Well, it worked. But the real epiphany for me was, hey, you can make a robot follow an invisible line, an internal line. And I think that's important. Okay, let's see where we're at. Okay, next thing I did, actually built the robot. And when I built it, the servo was a little twitchy, but it worked fine. It worked pretty much the way I wanted. And I had predicted that going around a 6-inch curve, that the servo would be offset about 3/8 of an inch. The line was an inch wide. And in fact, that's how I set the gain on the servo. I said, I know what an angle needs. I know how much I can allow to be off, so I know how much gain I have to have. And I didn't put any more gain than I needed because I didn't want it to oscillate. So basically, that was the way that went about it. So basically, I built it. It seemed to work. So the next thing was,
Didn't you care if you changed the
oh,
course?
basically, it looked twiggly, but then I tried to change the gain, the differential, I rigged it a little bit, and I took multiple ADC readings, averaged them. That didn't seem to make much difference. So the next thing was, of course, go to the contest and run the contest. And it ran the course, but it wasn't fastest, so I placed it. But then somehow along the line, I tried something. If you just reversed the motor on the drive motor and drove the robot backwards, and it followed the line backwards.
Was the dynamics about the same, forward versus back?
Or I can tell no difference.
Okay.
In fact,
Because it's the sensors in the middle.
Okay.
as a matter of fact, since I had holes and I could tell how far the robot went, I basically modified the program so it made about 2 loops of the stop, turned around, made 2 loops.
Nice.
So anyway, that's, I guess, probably the only unique feature about this robot. Of course, then the next thing happened is the PRG changed course.
I screwed up on you.
And they changed it from a black line to a white line, and 3/4 inch, which was not all that big of a problem. But they put the 90-degree turn. One thing, my robot, I didn't even design it to turn wheels. But it turns out that if you allow your front wheel to turn 90 degrees, you can spin around one point. And that's one difference between having a front wheel drive robot with steering as opposed to a car type where you have 2 front wheels and rear wheel drive. Because on a front wheel car, if you turn the wheels 90 degrees and try to push it. So basically that's one advantage to having a front wheel drive. Okay, let's see. That's it. Okay, so here's the lessons I learned. Not many, but there's what I said. First, I said the length of the robot should be small roads to the path. There's a little problem there. Is if your path has a fixed, you know what the path radius is. But nothing says the next course it won't decrease it
what does that say for the right angle?
That gets into the invisible line scenario.
Oh,
Go ahead.
Well, I guess that's basically one of the things, I guess, is a linear servo type line follower. It's good to follow a line which has a finite curvature, in other words, a smooth, continuous line with finite curvature,
Yeah.
preferably big finite curvature.
yeah, bigger the better.
And, well, one lesson then I learned that yes, you can locate the sensor between the rear wheel. And, that it can follow an internal line. Like I say, that to me was, at the time, I didn't really have any understanding of what it would be good for, but it just seemed neat to do it. And then the other one, is the fact that the change in the DPRG course made my robot fail. I realized that if you're gonna build a robot for the kind of courses we have, it's got to have more capability than a linear servo. Okay, so that's basically what I learned.
Yeah.
Maybe y'all already knew that, but,
No,
all right. So basically, the reason I labeled this speculation is one of our club members, Rainwater, kind of had the opinion that if the guy was spouting off on his robot and he couldn't show you the hardware, didn't believe him, put too much faith in it. Well, I haven't built this robot and this stuff, so what I'm talking is speculation, not real. Well, one of the things, and so basically the kind of my point here is DPRG courses is not really a line follow. And I don't really, what the closest name I can call up for it is it's called a route follower. And what's the difference, what is a route? You go from here to there, kind of follow, but you don't necessarily follow the line, follow a particular track. Okay, so basically the question is, what do you do about it? How do you handle this problem? What capabilities do you have to incorporate into the robot? That's the kind of subject of my speculation. In this book here,
right.
which, by the way, it's an interesting book. I found a couple of rather what I think are stupid errors, so I kind of question how, need to question some of the things. I think it was written by a professor and one of his students, so maybe the student part is
So it's, show it to the camera. Can the camera see a mobile robotic car design?
But it's pretty interesting. It does have a more complex model for the robot, and it also talks about when you use a camera to basically detect the line, how to transform it back or the honest way, I haven't read that part, so I don't know exactly what it's saying. Anyway, they made the point that there's basically three different kind of ways to get from here to there. One is just a waypoint. You go, only the one requirement, you start here and you wind up there. The other is basically following the line. And the third one is where you're following something, trying to track something. And if I'm not mistaken, I think Carl basically took the first approach. He set a bunch of waypoints on his line, and then each moved. Am I wrong or right?
Sort of. Well, it's more like, it's a combination of maybe of A and B, because the camera would look at the scene, and then based on that scene and recent scenes, it would say the most appropriate place to aim in that current image is here. And at that point, it would shut up its eyes and then just attempt to go to some fraction of that heading and.
So basically, you're doing the first. As much
But
as you can.
the first was how the commands were given to the wheels, but the determination of where is point B relative to A, that was
More like C.
more like B or C.
Okay. Well, anyway, the one point is you determine the waypoint, and then aim your robot and go
Yeah.
do it. That's one approach, and that works even though your line is not continuous.
Yeah.
It's got sharp corners,
Right.
because you're just going, but
But it's difficult to figure out where is it should aim.
Well, that's hard, and then it's also, it's not got anything, I mean, I would guess it's probably some kind of first order loop, right? I mean, and there's no deterministic algorithm for the control loop.
yeah, well, it's, once you set the point, yes,
It's ballistic.
No, you can servo it to that point.
Could,
You can
But you
close-
do,
can close
you
loop.
drive to.
You can close loop around it.
could.
Then for it. Then the last one there is similar to that, except instead of you target jumping like that, it continuously moves. And in both cases, you learn actually the robot, it doesn't necessarily follow the line. Because if, say your line has got an sharp angle in it, and you choose this waypoint, you choose a waypoint here, the robot doesn't
Yeah.
go to that corner, it cuts the corner.
Yeah, if your step size is too big, it'll ignore all the detail in between.
It basically smooths the curve,
Yeah.
which basically says gives you a robot, generates you it's a way to generate you a smooth path to follow.
Yeah.
Okay. Like I say, the last one is similar to it, except that the waypoint is continuously moving. And so if your sensor, and by the way, another point I've made is what point on your robot is trying to follow the line? Is it, what point on the robot in question is? Well, I'll get to that a little later. But anyway,
I guess for ours, it's the center of the field of view of the
Well,
camera, or
No, I
whichever
think
line.
it depends, because
Yeah.
for mine, it started off being, my initial simulator started by pivoting about the center of the field of view of the camera, which was, if this was the robot, my camera was looking down here, and it would pivot about this point, okay?
Right.
But I figured out at some point that when I got physical, that wasn't gonna work very well, because in reality, the pivot point wasn't up there, the pivot point was between my two wheels.
Mhm.
So I actually then, in the computation of the error loop, if you want to call it that, of where I said, like, I'm going to aim here, I need to turn so far and move forward so far, I actually changed the calculation of the angle it used to be from the bottom of the image to that point in the image. And what I did was that I put an offset in the equations so that it calculated the error from the pivot between the wheels.
Mhm.
So I actually did account for the physical, so I can move I can calibrate the robot now in a kind of crude way in terms of where is the camera looking compared to where it actually pivots.
all right. The last one there is if your camera is looking out in the front, forward, you can basically determine where the line is and basically aim for that point.
Yeah.
And that line, that point you're aiming for is doesn't have any mass. And so it can, quote, follow the line, but it can go along there and jump over here where the robot really can't. And so basically that's another way to basically smooth the path, is to actually follow it. And I think, was it Scott, who gave the last demo on, talk on robot following the line. Does that
That might be me. I
Yeah,
did,
right.
part of it was,
That's basically what you do, isn't it? You kind of choose a point out in front of the robot and then
Yeah.
keep aiming. And you always keep that point moving in front of you, right?
right, yeah, it's done, as fast as the frame rate, which you can set. I think that was
So
set
if
30.
the robot moves forward, your point you're trying to track stays in front of you.
Right.
So basically, it's kind of the last one here.
Yeah, I think it would be, yeah.
I mean,
Oh, that's what Carl's is too. That's what yours is too.
Yeah,
Well, okay,
you know, with just extra legs,
well, all right.
discontinuous legs.
Well, the other one is how do you actually make it follow the line, or if you can? You know, how do you solve this problem of, you got, your course is actually a set of
Waypoints.
line segments that are discontinuous. What, obviously your robot can follow the line as long as you got a line. But what happens you come to a joint? And the answer in this, I think, is what Doug does, is the servo goes open loop. When you lose the signal or you saturate it, the robot just goes open loop. And so what do you have the robot do when it goes open loop? Well, this is kind of how I think you handle the right angle. You go along here, and if the last thing you saw before you went across lost the line was you had something on this side. You tell the robot to turn hard in that direction.
Mhm.
And so it goes back, hopefully it will catch the line again.
Yep.
Doesn't come in too steep so it overshoots too far before it comes back. But
Yeah.
anyway, so basically that's one way to generate your smooth path or generate the path. So the question is, how do you generate a smooth path that approximates the course? And like I say, one way is when the servo goes open loop, based on what you think
Prior.
prior.
Yeah.
It either makes a turn, or if it doesn't see anything, it says it goes straight
Yep.
because it.
Assumes it's a
It's
gap.
a gap,
it's a
yeah.
gap. That works pretty good as long as yes.
It won't get your acute angle.
Well,
The
actually,
reason why the acute angle is because, like you say, when you're going and you didn't have any strong signal to either side, or essentially when you left the line, you were when you left the line was being tracked well. Otherwise the signal said you were on the line and all of a sudden there's no line.
Yeah, it came to the point.
All right, well, it turns out that in the acute angle, because it's a sharp turn, and your sample, lost line, but that last sample could or could not be, I'm right in the middle of the line. And so at that point it would say, I'm in the middle of the line, I lost the line, it's a gap, go straight. And that's why the acute angle is.
Well, yeah, it just
Now,
depends
for
on your
people that are
sensor.
using cameras, that are using cameras, it's a different story.
Right.
All right, but I'm talking about a traditional
Lines.
linear
Line
line
array.
3 or 4
array.
discrete elements.
Right, otherwise, I want to solve this problem, if I could, with just a standard line follower, just like you could do on any line follower. But there are, when we built the course, we put things in it that are hard.
Yep.
And
And are
I
still
mean,
hard.
Thanks,
on
Doug.
purpose, and that the acute angle is extremely hard because if you're doing a linear array, it looks like a gap.
Yep.
Unless you can catch that.
Unless you can, now how you can kind of do this is you can move back in time.
Mhm.
You
Yeah.
keep move back in time, and you can say, well, like 6 samples ago, hey, you wanted to turn left. But if on a true gap, 6 samples might say, I'm still on the line. So you can do that sort of
Yeah,
thing.
or incorporate a memory. Same
Yeah,
thing.
yeah, essentially.
You know, same
That's
difference.
memory.
Yeah, or you can use leaky integrators. Leaky integrators can also work too.
Or you can just use a camera and measure the angle.
There you go.
Yeah.
And then when it goes away, you go open servo.
Yeah,
Then you
yeah.
go, oh, that was
I
an idea,
feel that
130.
there's no question that the camera solves a lot of
It
issues.
does,
Oh, yeah.
it introduces a few, but
It
it
introduces
solves
a few others.
Yeah,
The question is, how many lines can your sensor detect at one time?
Like
It's really one.
his or mine?
His can detect a bunch of them.
Yeah.
Well, I mean, you've got a line sensor, and if you've got 2 lines under it, you get two LEDs, or
Yeah,
sensors.
two individual signalers.
Yeah.
2 blips, if
So how do
his.
you know which one to
resolution-
use?
Yeah.
Which one?
Yeah,
Well,
if you're,
okay, if you're
taking a bunch of them and doing an averaging,
well,
then you're
okay.
not getting
Here's
enough information.
this is one thing you can do. You can start looking at you look at the transitions from light to dark and dark to light. If they're an even number, okay, if they're an even number, then you know that you can tell whether the light is light or black, which is another issue in this thing. So then you know the line is either whether it's light or black. Where you really get into trouble is if you just catch the edge of a line, so you only have one transition. Okay, at that point you have to use historic information to know whether you're on a black field with a white line or a white line on a black field. So what happens if you do it right at the transition boundary of one block from another? Well, that's what I'm saying. It gets hard.
Yeah.
But there's tremendous amount of other information that's in your sensors other than just light and dark. You can use, like I say, the obvious one is the transitions themselves and how many you got. That tells you a little bit about your line.
And like you said, your history.
And your history. And you have to pull back in the history because there's if you look at the course, the challenge course, you can't come up with a rule like you would on a normal course where you would say, turn into the last line. It won't work
Yeah.
because there's places on the course that do the exact opposite.
Yeah.
Yeah.
Turn to the last line.
All right, next,
Yeah.
I guess basically, here's some questions I have. One is what, question I brought up before is what point on your robot is following the line? And does that point have to be fixed? Or can it move about on the robot? And does it even have to be under the robot? Can it be out in front? And so, like, basically, you know, can that enter into your thoughts? The next line of thought here is prior knowledge. You got, well, you may not, I'm not recognizing it first. Anytime your robot's going to do anything, it has to have some prior knowledge. And the question is, does the program, do you have it programmed in there, what I call explicitly, or do you have a model of the world? The assumption guy just hit the ceiling when you see that.
Yeah.
Basically, do you have a model of the world and then use that to make decisions, or is it built into your code? In other words, all these decisions you were talking about, you know, if all of this is, it's based on knowledge of the course, and the problem with using too much prior knowledge in your program, is prior knowledge tends to get stale. And
Yeah.
When they change the course.
and they change the course. So there's a question is, well, there's several questions involved with that is, how much should you use, or should you use it? Is it fair, or are you cheating? Are you not cheating if you use? Now, I think that basically you made the assumption, well, with the tiles course, every course could have, all had the same tiles, but they could be in any order.
Right.
With the banner, until the next
Do we reprint it?
iteration.
Yeah.
Or a little patch.
Already, so do you take that in consideration? What your, in other words, when you program it, do you realize, do you take advantage of the fact they are in a
Fixed
fixed
pattern.
I think you intentionally said no, but you said that you'd accept the tiles in any order.
Yeah, I consciously, I mean, me personally, I consciously tried to avoid putting things in that
Would care about
that
tile.
would care about tile arrangement. But implicitly, since that was the acceptance test procedure, right, was that one fixed course, you know, as you go from just like, okay, there's the forward direction, now what happens, it should be able to follow it backwards, right? Well, then you find out that, oh, okay, so implicitly, without realizing it, I had coded something in my allegedly androgynous algorithm that worked well in the one direction, but it failed in the other direction, and I just didn't realize it at the time. But, yeah.
So basically, the question is how much and how do you incorporate it into your robot?
Yeah.
So you don't want to get too far off course here.
And it's tough questions, right? Because how much time do you want to put into it?
Yeah.
Well,
How generic?
And do you, in effect, learn the course by trial and error, or do you essentially understand what the course is and based on the course, put the algorithms in?
Yeah. Or, you know, like, because what I attempted to do, I think, was the latter, because if you look at the rules, it defines the primitives for the tiles.
Yep.
So I took the approach of, if I can solve any of the primitives, and if I
Right.
can solve,
Yeah.
if I can solve the adjoinment of any primitive, then I should be as generic as possible
Right.
within the constraints of the primitives.
Yes.
And regardless of how much cheating you consider it, no one has actually, finished the course with cheating or without it. So
Right.
It probably doesn't matter at this point.
Yeah, thanks, Ray.
So,
Till we
I guess
finish.
one of the next thoughts I had is, what if you don't really consider it a line following, and you can have basically almost as much advanced knowledge as you know? Can you make you basically fix your computer or your robot so it can basically follow what I call Google instructions?
Yeah.
In other words,
Yeah.
tell it to follow the line until you come to a landmark. And based on what that landmark is and where you are on the course,
Yeah.
in other words, if Google says, and when you come to one of these squirrely patterns, you don't try to follow it.
You go to the next point.
Just go straight.
Turn right when you lose the line.
yeah.
You provide it with a pre-programmed
Yeah.
course,
Yeah.
an internal course, and say, follow this path that you have somehow encoded into your computer. So
Yeah, you
it
could
goes
do that.
along, and when it comes to the dotted S, it does something like this.
Move like an S, pretend that you're following it, and
Because, is that legal? Or harm?
depends
The
on
intent was,
It depends
at
upon
one
whether
time,
judges
I'm not,
catch you or not.
the rules was that you had to follow the course algorithm. Can't say the word.
Algorithmically?
Yes, thank you. Otherwise, the intent was, like now with what we've seen with donkey cart, it would be possible to train on the course a couple of times and follow it.
Yeah.
All right? But that's not what we really wanted it to do. We wanted it to be where you would put your car, if you want to do simulations, no problem. But when you put it on the course, that it is really interpreting the line, the robot real time. You know, it's not sitting there saying, okay, otherwise I'm in block one, go straight. You know, I'm in block 2, turn left. I mean, that's, you know, we didn't want to do it that way. Now, but at this point, we probably wouldn't care.
No. Well, hey, the donkey car is more or less a fancy convolution of a lot of photographs. So what's the difference if you decide to store an image of the course and an idealized path? I don't think it's too much different, really.
Yeah.
Algorithm, you know, it's still an algorithm. I don't care, right?
Yeah.
I
Well,
mean,
like I
it's just
said-
a little description of what it is. And really, what Will's proposing there, if I've got it right, is if you did have a model of the course that you're referencing, sort of like Tesla, car driving, whatever, you've got information, GPS information about where the roads are. So it's not a trivial task to do what Will's talking about, which is look for, what did you call them?
Landmarks.
Yeah, and correlate your model with what you're seeing and where you are and all that. That's a good problem to solve. And that's what's being done in these self-driving cars. They're not just out there driving the roads. They're taking in, they're weighing up what the GPS is telling them.
And looking at their road map.
And if there's a discrepancy, I'm sure they get nervous. You
Oh,
know,
yeah,
the road, you know, Google says the road turns left here with such and such a radius, and I don't see it. I'm probably going to put the brakes on. Recalculate, yeah.
Yeah, recalculating.
Yeah,
Anyway,
Ron,
that's what's
I
fun about
agree,
this.
and what I'm just saying is, when we first started this path, this journey with the challenge course back in 2011, I don't think anybody thought it was going to be as hard as it was.
I thought it was hard because it didn't look like something that could be solved just right away, and I'd rely on being able to sit down for a few days. Otherwise, go back after the thing after a year or whatever,
Yeah.
and stuff.
And I just wanted to make an observation. One of the things I love about the club is a really great presentation that morphs off into discussion, which is really interesting and very related to
Well, the other thing I'd say too is that there's a lot of different people going at it in a lot of different ways, and I think that's good too.
That's fun.
Yes.
Okay, Will's got a book.
Got another book here, which is just basically, I think, what they had a
Hold it still.
symposium or some, had a symposium or something like that.
You got it, Deb?
And-
I think so.
and then-
Who's the author? Does it say?
Okay, wait a minute, I'll look and I'll tell you. Author is, well, edited, wait a minute. Edited by, where's the author?
Well, it's a bunch of papers.
Oh, I see, okay.
It's a collection of papers, right?
So Oliver Brock, Jeff Trinkle, and Fabio Ramos.
Put it to the front and let me see if I can get it.
Okay,
Fine.
Yeah, I got it.
MIT Press.
Okay. All right.
There's a number of papers in there that maybe have some relevance to this.
Yeah.
There's one in there on the group that did the urban challenge. They talk about how they followed, how they defined the path. And here again, while they didn't really say it, their approach is to look out in front and create a path
Yeah.
and then follow it. And the fact of the matter, I think you put a link to the Tesla picture.
Yeah.
And if you notice, there's a red line down the middle of it.
Oh, yeah.
And I wondered who put that red line on the road, and it's not.
No, right.
That's
That's the
Tesla's.
rest of it.
Tesla's.
And you notice that red line did not stay fixed in the field of view. It was moving around.
Yeah.
So basically, the car, they were following that line, but they were not trying to follow it out there. They were following.
They were creating, as I understand it, they would create a state estimate of the road, and they would create a target path along the state estimate of the road, and then they would follow the target path.
All right, I think we've wasted enough time, except we do have a simulation we showed, which basically the idea is in order to get the delay of interpreting the image out of the loop,
Yeah.
what you look out in front, decide where the point is, and you put it in a map, internal map, and then later, when you get, you basically know where that point is, and you use it and then to try to follow that line that you generated. In other words, the sensor out in front is generating an internal line that the robot is then following with the virtual sensor.
And that,
makes
yeah,
sense.
and that line, in this case, in this diagram, we're seeing, when I reset it, green cookie, or green little circles. Those are the camera sensed cookie crumbs. And the sensor, hang on, let's see if we see it in this illustration. We see it? Wait.
And can you tell us what this is written in?
Processing, and it's, I published it to my whatever, GitHub, so you can pull this and look at it. I was gonna talk about it, but I don't know if we'll have time today.
So the crumbs are the line?
The green, yeah, are the cookie crumbs, and those are, that circle is sort of the detector, which is sort of like maybe a video camera.
Mhm.
But the blue, the magenta line that you're seeing across the robot, that's a virtual sensor, and let's see if we're not tracking at the moment. Hang on, let me reset when I slowed it down. Okay, hang on, let's see. Oh, maybe because I'm going slow. But that magenta line is a virtual sensor. But, so in other words, are we tracking? No, hang on, okay.
It runs as well as your robots, Ron.
Yeah, hang on.
It's a good simulation.
Yeah, perfect simulation. I know, the space bar toggle can follow. There we go. So anyway, so what's happening is that you can see the camera is picking up the line way out in front of the robot, but we're dropping those crumbs into a world coordinate system, which then we know where the robot is in a world coordinate system. And then those magenta sensor doesn't exist, but it's our virtual sensor in this case. So you can place that anywhere, between the wheels, wherever you want. And that's kind of an interesting idea, and that was, what do you want to do, Will?
Start it over again.
Uh-oh, did it drift
Ron,
off?
could you back up for a minute?
Oh,
So
what's that?
the crumbs,
Yes.
the green, so if the white circle, the white circle is the camera sensor, or the white circle is?
Yeah, the white circle would be, let's say, the
Like your
rule
field
I'm
of
using
view.
right now is cheating a little. What I'm looking for is the nearest crumbs. What happened? Uh-oh, we missed. Wait a minute.
The robot's
Spazzing out.
The robot went away, but the dots
kept
continued.
falling.
Yeah, wait a minute. And I am being cute. I'm fading. Oh, okay, it's a little tough for that.
You get a loop issue.
Kind of a little loop issue. No, that's kind of a hard bend there. Let's see if we can, did I add anything
gain on
to
the turn
that?
isn't
Slow it down. Hang on.
He's not, yeah, he's lost it.
Just a few
Yeah,
more
hang on.
adjustments to the code.
Hang on, let's see.
It needs some more D in that thing.
Yeah, sure does.
Crank up the derivative.
Now, are we following the line or not? Wait a minute.
It's a smop, right?
The wheel isn't going back and forth.
Yeah,
There he goes.
hit it this time. Come on, baby. Come on,
Yeah.
that's it.
Yeah.
Come on.
Yeah, but
Huh?
How is it in
Lost
turn
selection
right?
there?
Oh, and I killed the path
From
back
the
in.
magenta.
Oh,
But that's virtual, that's not an actual.
no, that's virtual, but it doesn't matter. In other words, the detected crumbs are dropped into the coordinate system of the robot. Imagine as if you just literally dropped a cookie crumb where that camera was seeing. And then the sensor back there gets to see those cookie crumbs.
Okay.
But you don't have to do it in reality. Like Will was saying, invisible lines aren't bad.
But isn't the circle what the camera is
Is
seeing?
the line?
Yes.
I'm confused there.
So that as you're going around this spiral here, the camera hasn't seen any of the cookie crumbs, so how?
No, no,
What it's
the
doing,
camera-
sorry, it looks a little bit confusing.
The
The circle, we're
camera-
computing the nearest point on the line, we'll say, which is the yellow dots. The nearest point, hang on, let me reset the thing.
Okay.
So in other words, I'll freeze it, let's see.
Just a second.
So,
The
let me just point.
line is your sensors, right?
Yeah, so anyway, these yellow dots indicate a line. Okay, now we could get cute here and we could draw a physical line and physically process the image or whatever, no big deal. Okay, but so for this illustration, the yellow dots indicate where the line really is.
Yeah.
Okay, and that we'll say is in world coordinates. And I'll say something here in a second, but anyway, so right now, the closest line point to this circle is that right there, and there's the green dot. Okay, and I'm now calling that a cookie crumb. But that cookie crumb is, we calculate based on where the robot is. The robot, and this is a little tricky because the robot, we put it in a world coordinate system, I'm going to say. In other words, the problem is as the robot drives along, let's see how to say this, because of odometry isn't perfect. A robot, if we start driving around in this room, might get slowly error will build.
Yeah.
But with respect to this, what's really important here is the camera sees this point, we'll say, and this point, it's 10 inches out in front of the robot.
Yeah.
The cool thing is that if the robot thinks I'm here at, I don't know, 0.20 or whatever in the XY coordinates, and 10 units out ahead is that cookie crumb, it can now position that in the world coordinates, and it's pretty accurate. I mean, real accurate, in fact. And what we're really worried about is just for the time that that robot is going to drive about the next, we'll say, 6 inches, is what it really matters.
Yeah.
And so what we're doing is we're able to put a point and know exactly where it is with respect to the robot and drop it into a physical list such that we can drive along and follow those virtual cookie crumbs as if they were real, because they are, for all practical purposes, they are. In other words, we're storing them in memory. It doesn't matter.
Okay.
Now, does that matter? If I still have
I put it a little different.
Okay, he'll put it.
The robot is detecting the line out in front.
Yep.
And it's doing it in robot coordinates.
Yep.
It knows, oh, okay. But the robot knows its position in the world.
Yeah.
And so that point
Yeah.
is transferred to world coordinates.
Mhm.
So it's now stored that point in world coordinates. The robot moves, detects another point, stores that point in world coordinates. So it's creating a map in world coordinates. Then the robot is moving, the virtual detector back here
Yep.
is taking that
line.
It's stored.
It's stored
In
in,
consulting.
it's stored in world coordinates, converting it to robot coordinates.
Well, not,
and-
sorry, not this program, but that's okay. You could do it that way.
Converts it into robot coordinates and then sees how close the robot is to that line.
Now, if I understand, what's the sensor is what up there in your picture?
Oh,
That's
The purple one. There's two sensors.
The one in the
the one
front is
now.
kind of hokey, let's put it that way.
okay.
Yeah.
Well, I mean, I could show you this in a real beautiful OpenGL 3D simulation if you want to see that.
No, but
Okay.
where is its field of view?
Well, okay, it's using a rule. What I did is to just get this done quick, whatever it was, February, whenever I wrote this. What I did is I just made up a rule and I said, look, I'm going to put a sensor disk out here, and my rule is the closest. I'm going to cheat because actually this simulation, I can consult this entire list. And I just asked the question, what's the nearest line point to that disk? But if we had a field of view of a camera, we could do the same thing, could we not? If the camera was looking out there,
Right.
and we could go from the center of the image and say,
Right.
what's the closest line point
Yeah.
in that field of view?
Well,
Okay.
the thing that was bothering me in some sense is what's the extent of the field of view? Because,
Oh, it's infinite.
okay,
Yeah, it's,
all right.
well,
You find
no, oh,
yeah.
I could be lying. I may
Oh,
have a
what, would you?
limitation. Yes, no, it may have a limitation. But
Yeah.
what it's, as long as the robot is sensibly oriented, it's gonna find a sensible point.
Right, but I'm saying that circle doesn't represent its field of view.
No.
But I mean, the field of view is much bigger than
Yes,
this.
yes,
Okay.
very good.
So that was the first hang-up I had, but then the other hang-up I had is that, if I understand what you're showing, when you're closing the loop, so you determine the error in heading, that error in heading is not based on the cookie trail that's out in front, it's based on where is the cookie trail at the virtual sensor.
Right,
That took me a while to,
yeah,
Close the
and
loop
that's
on.
the whole point of it. That's the beauty of it,
yeah.
is you can look, go ahead.
The point is, there's a time delay.
Yeah.
You find the cookie here,
Yeah,
and you use it later,
right.
which is how long it took the robot to get there. And so during that time, you can, first off, it gives you time to actually take your data and
Massage it.
massage it and get yourself the point, however long it takes you to find out where the point really is.
You've got to bake the cookie before you eat it.
And also, since you have a series of data here, it's possible that you can filter that data.
Yeah, clean it up a bit.
So,
You can get the curves out of it.
Ron, one question. You said the cookie crumb is put where the circle finds the yellow. I assume you mean the center of that circle finds your
Well,
line?
the closest line point, we'll say, path point to that,
To the center.
to the center. Yeah, so in other words, if it was a camera image,
Right.
obviously it would have some limitation in field of view. Then what we might, the rule might be, what chunk of line do we see that's closest to the center of the camera view? And wherever we find that location, then even if it's
That's it.
many visible, we would pick that one and say,
Drive
you know,
to it.
yeah, well, that's the location. Now, we have a problem, we have other problems. This was about if you kind of knew what the path was. Now, obviously, show the camera whatever, the boundary of an inverted tile, we got
Yeah.
another problem.
I mean, this is the kinematics part of it. The other part that this kind of blows off is how do you interpret the generic image?
Right.
And how do you tell
Right.
what is the
How do we
line?
get to this?
Yeah.
So this is just the second example here is same idea, but here we have an idealized course path. Now, we're sort of avoiding the part of getting from the part we need to talk about, which is perceiving and getting to this.
Yeah.
But ideally, I think this is what Will is ideally saying, that we need to get to here, more or less. Would that be a good idea for, this is now defined in terms of something we can't follow. This is a line following problem now.
You're following-
If we can get to this.
Following the cookie crumbs.
Right, if
all
we,
along.
now, the other thing is perceiving where we think the path should be, because obviously I've idealized, like the S curves, I've faked them a little bit. I've made them into something that's more followable, and Will made a perfect.
Running out of time.
Well, no, what's going on?
No, you got plenty of time.
Well, let me see.
Oh, okay. Oh, you need to go play by.
Yeah, I got it.
See you do.
Thanks a lot.
Oh, you bet.
This sensor that he's got in front, it's, in my opinion, it's hokey.
Yeah.
But what I'm started messing with, and I don't know how well it'll work, but I'm saying that I have a line sensor that's an arc.
Mhm.
And I think it needs to be close to 180 degree arc,
Full hemisphere, okay.
on half circle,
Yes, sir.
with the center of the arc approximately at the center of the virtual center. I mean, virtual.
Turning radius.
So that the distance from that point to the virtual center is basically
The same.
the same.
Yeah.
And this curved sensor then moves along the line. And it will cross the line, most of the time it crosses the line once. But there are cases when you get the
Acute angle.
acute angle, it actually crosses the line 3 times. But you're only looking for the one closest to the center, because that one, if you just plot that one that goes in the center, I mean, the closest to the middle, when you come to that point like that curved arc,
It'll close up quickly.
No, it won't, it never really, it goes, you got the one over here, but the one in the first one out from the center
Yeah.
is the line, is the closest point on the line. They're both on the line, but the first one on the arc is the first one you come to when you're going on. So
Yeah.
I think basically that.
Okay.
That
Yeah, I
way-
was thinking of a angle like this, but similar.
Anyway, I think
Yeah.
that basically, if you use that kind of sensor
Mhm.
if it can detect what is line and what's not line.
Yeah.
If it's detected line, then it lays a chrome down.
Yep.
And then put some kind of filter in there to basically take the kink out of the line, and then let the virtual sensor follow the line. I think that's enough for me.
That's cool. Yeah.
Cool.
And I guess where you have a gap, you just keep going.
Yes.
If you think
Well,
about that, that's the ideal
Because
way.
that's part of what you do. Your internal map will have a gap in it. But one of the things you know is that basically they're kind of spread in time. So all you really want to do is fill out, put some points that connect it
Yeah.
in your list that are not spaced too far apart. And that brings up the question, how do you store the internal map? This program basically treats it as a bunch of points.
XY in known world space.
But,
Yeah, or robot space.
Or robot space.
but then you want to get more sophisticated and have a continuous line somewhere.
You know, if you did have a sensor that was, you know, the
Like
right,
an arc.
like radius of, you know, 180 degrees, I think that would work at catching all those acute angles
Yeah.
easily, because you could come up and you'd know, it would just shift from the center of the line, or the center sensor, off to one either to the left or the right, but it would still sense it. It's not like it would all of a sudden, be there and then disappear if you had a linear, or, sensors all in a line. That's a neat thing. I wonder if we could do that with our cameras, though. That's a little more difficult.
Yeah, no, that wouldn't be hard at all,
To sense, well, I guess you'd have to do line segments to sense in,
You
right?
just,
Well, except
the
if you're
specific
gonna do it all
pixels,
the way around, you have to put the
the
camera
specific
above, but-
pixels.
Well, you can do the camera above with perspective correction, like I do, and
Yeah.
you could get an arbitrarily shaped sensor curve with
I
a
guess,
mask.
yeah.
Yeah.
Oh, that's true,
You
yeah.
just make a mask, and
Yeah.
then
Hmm.
Yeah.
boom, you're done.
Yeah.
Hey, Coach, I've got a
Wheels
question.
are turning.
What would happen if one of your good friends from DPRG were to go ahead and make the 1-inch line, and just before you reach the end, that one line basically veers into two, so that there's basically two finishing points. Either one's correct, but that one line now.
They have that case already. You mean a
So-
fork in the road?
Well, not necessarily, no, not a degree.
it's
So,
two forks.
No,
curve.
Just a
So,
second,
a
go
nice
back to
curve.
your.
Yeah,
go back to
So
the-
what would,
There.
What, right here?
The
Is
EVE
that right
Force
there?
designers already did that.
See right
The
there.
Eve
Okay,
was-
I thought that was multi-level. I thought it was going up and going
Oh,
over.
no, no,
Okay.
well, in this case, you're supposed to make a right turn at this.
There's,
Yeah, you
got
must,
these two
must make two
junctions.
rights, yeah.
there's
Prior
one entrance
knowledge.
and ABC.
So what would your device have done when it comes to that?
Well, you'll see, if you had any kind of a linear sensor or a scan line, in that case, a scan line would catch that, where you'd see you'd be seeing a single blob in the center, and then suddenly
Two
you'd
blobs.
see multiple.
Yeah,
blobs.
right.
And then you know, oh gee, okay,
What
that's
do I
a
do?
fork. And then you have a
Fork.
rule, take the right turn,
Oh, okay.
So then you go for the right. Whereas the other one, where you're coming into this acute angle here, this
Yeah.
tile right here, looks more.
You still turn to the right, though.
In this case, suddenly,
If you go
you
forward.
see two,
Oh, yeah?
two lines. The one you're closest to and the one's approaching from the right, and it's getting closer and closer. Then you can say, and then the line disappears, and you know you got it, so you just
Let me ask
execute a
you
right
this.
turn.
If you wanted to go to the next town, you ask somebody how to get there, and he says, take this road. And you get on that road and you travel along there, and it farts. What do?
Yeah. Take the right
Follow the
forward.
Yellow Creek Road.
There you go. Take the right forward.
The answer is, you know,
You gotta make an educated, make a hypothesis.
Or
No.
priority knowledge.
Yeah.
the only way you
The
can
guy
get
told
solved
you,
that problem is
you
have
stopped
some-
at the gas station, well, when you get to the fork, you
Fork
take the
road.
right.
Well, actually, it has to do with, in my opinion, how local is your sensor information.
Yeah.
In other words, if your view is only quarter of a mile or half a mile, you can't tell where those go. If you're up in an airplane up there looking down, you can tell, I mean,
Yeah, you can see.
so the
Yeah.
answer
You
is.
see the whole map.
You see the whole map.
Well, I was gonna